Okay, the next question is find the average kinetic energy of the particle in a 1D box of length L in its ground state. Now we have already done a particle in a 1D box. We have solved the Schrodinger's equation for particle in a 1D box of length L and it is in the ground state. We need to find the average kinetic energy of the particle. So the wave function for a particle in a 1D box is given by psi x equal to root 2 by L sine of pi x by L. Remember, the wave function was n pi x by L, where it is said that the particle is in the ground state, so n is equals to 1 for ground state. Remember, n, the minimum value of n would be 1. For ground state, n is 1. It cannot be 0. So psi x is root 2 by L sine pi x by L. So this is the wave function of the particle in a 1D box of length L. So the kinetic energy operator is T, and it is definitely moving in the x direction. So the wave function is a function of x only. So we'll take only the x directions momentum operator. So the kinetic energy operator is px square by 2m, where the px operator is minus I h cross del x. So if you square it up, minus square would be plus, and this is imaginary iota, its square would be a minus. So it is minus h cut square by 2m, minus of h cut square by 2m, del square del x square. So this is the kinetic energy operator in x direction. So we need to find the average kinetic energy of the particle. So if you take the average kinetic energy, again, to find out the expectation of any operator or any observable, you need to sandwich it between psi star and psi, this operator, and integrate within proper limits. The limit would be 0 to L since the particle is in the 1D box of length L. So psi is again a real number, a real quantity. So it is root 2 by L sine pi x by L. And I have put the kinetic energy operator minus h cut square by 2m del square del x square. And again I have put psi root 2 by L sine pi x by L dx. Now you can take the constants out. I have taken minus h cut square by 2m. Root 2 by L can be taken out. So it is 2 by L. 0 to L, it is sine pi x by L, sine pi x by L, and this operator del square del x square will first operate on this and then it will be multiplied. So always remember this. So sine pi x by L del square del x square of sine pi x by L. So if you differentiate it once, you will get a cos pi x by L with pi by L out. And if you differentiate it again, you'll get a minus sine pi x by L with a pi by L out. So you get a pi square L square out of this differentiation, and there would be a minus sign, because if you double differentiate sign, you'll get a minus sign, and here is a minus sign already out, so it would become positive. So pi square L square would be out, h cut square by 2m is already there, root 2 by L is there. So you have a sine pi x by L, you double differentiate it, and here there is a sine pi x by L. So you have a sine square pi x by L. So I'll take 2 inside, so I'll have a 2 sine square pi x by L. So here, what I've done is, so you have L out, so there is an L square. So L square and L, you have L cube, pi square, h cut square, the constants are here. And I've taken this 2 inside to make it 2 sine square pi x by L, so that I can put the trigonometric formula. So it is again pi square h cut square by 2 L cube m. 2 sine square theta is 1 minus cos 2 theta. So I have 1 minus cos 2 pi x by L dx. Now if I integrate it, first will be dx minus cos 2 pi x by L dx. And if I integrate dx, I'll get L within limits. And cos 2 pi x would be sine 2 pi x by L by 2 pi by L. Now if you put the limits 0, sine of 0 is 0, and if you put L, L and L would get cancelled. Sine of 2 pi is again 0, so this term will be 0 altogether. So we have L cube, and L would get cancelled out. What you get instead is pi square h cut square by 2 ml square. So this is the kinetic energy operator. The average value of the kinetic energy. And remember, if you remember this, then the energy of a particle in a 1D box was n square pi square h cut square by 2 ml square. If you refer to the notes, the energy of a particle in a 1D box was n square pi square h cut square by 2 ml square. And here it is in the ground state, so n is 1. So the average kinetic energy of the particle is same as the ground state energy. And remember, a particle in a 1D box was free to move, so the potential energy was zero. So definitely the average kinetic energy must be equal to the total energy, since the potential energy is zero. So if you remember the Schrodinger's wave equation, we have put V equal to zero since the particle was considered to be free. And in ground state, the total energy was definitely pi square h cut square by 2 ml square, and that is definitely equal to the average value of kinetic energy since the potential energy is zero. So from this, if I ask you what is the expectation value of px square, just the momentum, x direction momentum square, all you need to do is you just have to omit this 2m, because the kinetic energy operator was px square by 2m. So if you just remove this 2m, you would get the expectation value of the momentum square operator. So it would be pi square h cut square by L square, because if you have a 2m down, px square by 2m is nothing but the kinetic energy operator. So just the 2m would be removed. So this was the expectation value of the kinetic energy operator. Now the third problem, which I feel is the most important problem in quantum mechanics. First, we'll read the problem. Suppose a particle is in a superposed state where it is given a psi equal to a psi 1 plus b psi 2, where a and b are some constants. We'll find out these constants, with e psi 1 as e1 psi 1. Remember, e is the operator e, so if you are operating e on psi 1, you'll get the value e1 psi 1. I repeat, you operate the energy operator on psi 1, you'll get the value e1 psi 1. Similarly, if you operate the energy operator on psi 2, you'll get the value e2 and psi 2. These e2 and e1 are the values of energy values. So you are operating energy operator on psi 1. So let us say if the particle is in state psi 1, and if you are measuring the energy value, you have to operate it with the energy operator. The energy value that you would get is E1. So state psi 1, a particle in state psi 1 has an energy value E1. Similarly, a particle in state psi 2 has an energy value E2. So, but what we have in this problem is that psi is a superposition of psi 1 and psi 2. So the particle is neither in psi 1 nor in psi 2. The particle is in a mixed state, you can see. It is in both. That is the beauty of quantum mechanics. Right from the start, I told you students, this is the weird and the most strangest part of quantum mechanics, that the particle can be at multiple states simultaneously. So the particle, if somebody asks you what is the state of the particle is psi. The state of the particle is psi. It's in both psi 1 and psi 2. It's in a combination of psi 1 and psi 2. So it's in state psi. Now it is given with a probability, 30% probability of measuring the energy E1. It means that if you measure the energy, see the particle is in state psi, it's not in psi 1. Had the particle been in psi 1, every time if you measure the energy, you would get E1. Had the particle been in psi 2, every time if you measure the energy, you would get E2. But this time the particle is in a combination of psi 1 and psi 2. So if you measure the energy of this particle, which is in state psi, not in psi 1 and psi 2, it's a combination of psi 1 and psi 2. So if you measure the energy of psi, 30% probability is you would get E1. So let's say you are measuring 100 times the energy of the particle, which is in state psi. 30 times you would get E1, and definitely that means 70 times you would get E2. So the probability of getting E1 is 30%. It is given in the question. Find the value of the constants A and B and also the expectation value of the energy. This is what you need to find out. So let us proceed. And one more thing, this is a very, very important point to note. Note psi 1 and psi 2 are orthonormal wave functions. Now, I'm coming to the solution of it. What do I mean by orthonormality? By orthonormal wave functions, we mean that, let us say you have, this is suffix m, this is suffix n. So you have psi star m, psi n dv, that is the elemental volume, integrated within proper limits. You will get a Kronecker delta mn. This symbol is called the Kronecker delta. What do you mean by the Kronecker delta? The Kronecker delta will have a value of 1 if m is equal to n. So if these two are same, then it is 1. And if these two are different, then this is 0. So please understand what does orthonormality means. If psi m and psi n are same, then it is basically psi star psi, m and n are same, dv, and this would be equal to 1. And this is the same as the normalization condition, you remember. Psi star psi, that is psi m star psi m dv, is 1. M and n are same. This was the normalization condition. And if they are different, then this is going to be 0. What do I mean by this physically? Please understand this physically. This means the state the particle is in. And this is the state where you are measuring the particle. So let us say that the particle is in state psi n. And if you are measuring it in psi m, then you would get a value 0. The probability of that measurement would give you 0 because the particle is in psi n and you are measuring the particle in psi m. M and n are different. So the particle is in psi m, n, and you are measuring it in a different state, you would definitely get a result of 0. The probability of finding the particle is 0. But if the particle is in psi n and you are also measuring it in psi n, these two are same, then you would get a 100% probability of finding the particle. So this would be 1. I repeat, psi n, if these two are different, then the particle is in psi n, you are measuring it in psi m, different state. Definitely the probability of finding the particle would be 0. But if they are same, you are measuring it in psi n, the particle is in psi n, and you are also measuring it in psi n, the same state, they are same, then the probability of finding the particle is 1. So that is what the orthonormality condition means. So if they are different, it would be 0, this integration value, and if they are same, it would be 1. So what do we get? Psi, if you normalize psi, let us normalize psi. So it is minus infinity to plus infinity. Psi star psi dv must be equal to 1. This total psi. So if I put psi star, I would get a star. Let us consider a to be generally complex. So psi star would be a star psi 1 star plus b star psi 2 star. Just the complex conjugate of this whole thing. And psi is the same, a psi 1 plus b psi 2. dv is equals to 1. This is the normalization condition. So take the first integration. We just multiply each term. So a star a would be mod of a square psi 1 star psi 1 psi 1 star psi 1 dv integration. Next term a star b psi 1 star psi 2 psi 1 star psi 2 dv. Next is b star a psi 2 star psi 1 dv, and next is b star b, which is mod of b square psi 2 star psi 2 dv. Now see this, psi 1 they are same, so this integration would be 1. Psi 1 psi 2 they are different from the orthonormality condition, they are different, this would be 0. Psi 2 star psi 1 again different, this would be 0. Psi 2 star psi 2 same, this would be 1. So this is 1, this is 1, this is 0, this is 0. So you have mod of a square plus mod of b square equal to 1. So remember, what was 1? What was 1 in our normalization condition? 1 was 100% probability. This was the total probability of finding the particle. So this 1 represents the total probability. And here you have summation of two numbers. So definitely mod of a square represents the probability of finding some observable if the particle is in psi 1. and mod of b square represents the probability of finding some observable if the particle is in state psi 2. So we have already given that the probability of finding the energy E1 is 30%. So again, mod of a square is the probability, because the addition of these two probabilities would give a 100% probability. So the probability of finding an observable if the particle is in psi 1 is mod of a square, and that is 0.3, 30%. Definitely that means mod of b square is 70%, that is 0.7. So you directly have a as root of 0.3 and b as root of 0.7, provided we consider a and b as real numbers. So we directly have these a and b. That was the first part. Find the constants a and b. So we have found out the constants root of 0.3 and b as root of 0.7. So I repeat, this is the total probability of finding the particle or finding an observable. This represents the probability of finding an observable. In this case, it is the energy. This represents the probability of finding the energy or getting an energy value if the particle is in psi 1. So what is the probability of getting that energy value E1? It is 30%. And this represents the probability of getting an observable value, in this case again the energy, if the particle is in psi 2. So what is the probability of getting the energy value E2 if the particle is in psi 2? And that is definitely 70%. So mod of b square is the probability, remember, and mod of a square is the probability, not a and b. A square is the probability, b square is the probability. So 30% is a square, or 0.3 is a square, 0.7 is b square, so a is root 0.3 and b is root 0.7. Now the final part, what is the average value of the energy? Definitely, if you measure the energy 100 times for a particle in state psi, the particle is in state psi, if you measure it 100 times, 30 times you would get E1, and 30 times, because the probability of getting energy E1 is 30%, 30 times you would get E1 and 70 times you would get E2. So what is the average value of energy? So it is the probability of getting E1 plus the probability of getting E2. So what is the probability of getting E1? 0.3 E1. And what is the probability of getting E2? 0.7 E2. Remember, I told you, so this is just for your explanation. For example, you make 100 measurements, out of which 30 times you get E1 and 70 times you get E2. This is what is given. 30% of the probability of measuring E1. So 30 times you get E1 and 70 times you get E2. So if I ask you what is the average energy, the average energy is 30 times E1 plus 70 times E2 divided by the total number of observations that you make, 100 measurements. So this I can write it as 30 by 100 E1 plus 70 by 100 E2. That is same as this, 0.3 E1 plus 0.7 E2. That is the average value of energy. So this is, students, this is probably the most important question from quantum mechanics. Thank you. So we end quantum mechanics over here.